Welcome to the second of my series of lectures this academic year, and thank you for coming along. This year I'm taking as my theme some examples of using mathematics in different areas, and today's lecture is about cryptography, the science of transforming information so that it can't be read or understood. And I'm going to look at how this subject has developed most surprisingly, because it's a subject that has secrecy at its heart, and yet it is now exposing its techniques, its algorithms, its methods to public scrutiny and to public analysis. But what is certain is that for centuries, massive intellectual effort has gone into methods of securing secure communication and secure storage of data, because of its importance, as you all know, in diplomatic, commercial, military and economic affairs. And we do know what the consequences of secure communication being broken can be quite considerable in both economic and in personal consequences. So let me start by giving you an overview of the lecture. Pause on that, escape. And there we are. So I'll introduce initially some of the key terms and the guidelines, and as with every subject, cryptography has its own language, its own notation, its own concepts and core ideas. And I'm going to focus particularly upon the idea of a cipher system, and that's what's going to run through the lecture. That's going to be the core notion. And it's got associated ideas of encryption and decryption keys. And what I want to do is to talk about some of the standard assumptions that are made about cipher systems and about the different ways that you can attack them. And the other distinction I want to draw out is the important and increasingly important one between conventional cipher systems and the relatively new public key approach, and talk about the seminal paper that introduced that. The first particular example of a cipher I'm going to look at is a very straightforward, easy one of no practical use whatsoever, the Caesar cipher. But what it does do is to illustrate some of the ideas I want to bring out about keys, key concepts and concepts about keys, and the potential weaknesses that there are in cipher systems. Then I'll go on to a class of ciphers called substitution ciphers, and these ciphers have a large number of keys, an astronomical number of keys, something like 4 times 10 to the 27. But it's extremely vulnerable, and it's vulnerable due to the statistics and the structure of the English language. And I'm going to be using it as an example of the fact that a large number of keys if you have a large number of keys, it doesn't follow that you have a secure system. In order to try to avoid the consequences that English has got a language and the statistics associated with it, we're going to look at the next approach of polyalphabetic ciphers, which are introduced to try to hide the statistics and the frequency analysis approach. Then I'll look, because it's such an exciting story, at the one implementation of the Enigma Machine, which is an electromechanical rotor machine and very important before and after the war, and about which Turing and Bletchley Park did a lot of work. But what I'm going to do is to look at another story that isn't as well known, and is how the Polish cryptographers broke the Enigma machine in the 1930s. But in my large picture, what I want to show from that story is that they didn't actually break Enigma, they broke the way Enigma was used. It was very heavily dependent upon the way that Enigma was used to set up the keys for any particular day. Then going on to modern ciphers, which are all electronically based, and they hinge around binary representation, the way that information is represented in a computer. And there are two main subtypes, cipher systems and block ciphers. And the cipher systems are very good for things like digitizing speech, although it doesn't seem to have stopped the Americans listening into French conversations. And what they do is they act bit by bit on the message, and therefore you do not have any error propagation if there's a mistake in transmission or whatever. So that's why cipher systems are particularly useful there. And the other type are more used for when you're trying to hold data securely, or to make sure that data is authentic and hasn't been interfered with, and they are block ciphers, and they can be made to depend very much upon what went earlier on in the message. Then I'll come to the seminal paper, the paper by Whitman Diffie and Martin Hellman, and that really is the beginning of modern public key cryptography. But again, we'll be able to see from my diagram of the cipher system, which is coming up in a moment, the very simple basic idea that they use to kick off this whole idea of making more and more and more of a cipher system public. Right? And it's all based upon the idea that in mathematics, it is believed that there are certain one-way functions, trapdoor functions, mathematical functions that are easy to calculate one way, but if you know the answer, it's very hard to go back to the input. Right? And at the finish, I'll just show quickly how the idea of public key cryptography can be used to provide digital signatures, which are the digital analogue of the ordinary written signature, and in fact can also provide, again, security that the message has not been interfered with and changed. So here's my core underlying idea, the notion of a cipher system. And two people, usually called Alice and Bob, Alice on the left and Bob on the right, wish to communicate securely. So Alice wants to send a message, usually called the plain text, which will be converted into ciphertext or a cryptogram, and she wishes to send that to Bob. In order to do it, she uses two things. She uses an encryption algorithm, something that she does, and that encryption algorithm makes use of an encryption key. That converts the message into another form, which is transmitted to the receiver. And of course it could be intercepted on the way, and you usually call the person who does the interception Eve, because Eve is an eavesdropper. Good, isn't it? And on the other side, what you have is a decryption algorithm. An algorithm is just a process of what to do, a recipe of what to do, and that takes as part of its input, takes as its input the cryptogram and a decryption key. All right. Cryptography technically is the science of designing cipher systems, and cryptanalysis is the science of finding information about the plain text without any knowledge of the decryption key. And cryptology is the term for both of them. Now, the keys are crucially important for the security of a cipher system, and modern approach very much hinges in a cipher system security really resting on the significance of the keys. Well, we can infer one thing from this particular diagram, and this is at the basis of the Diffie-Hellman approach, which is that in order to obtain the plain text, all you really need to know is the decryption key. You don't need to know the encryption key. And in public key cryptography, the only part of this diagram that is secret is the decryption key. In public key cryptography, everybody knows the encryption key, everybody knows the encryption algorithm, everybody knows the decryption algorithm. The only thing that is unknown is decryption. It's quite a surprising notion. Well, because of that, cipher systems are usually divided into two types. There's the conventional ones, which are also called symmetric ciphers, and that's one where it's easy to deduce the decryption key from the encryption key. Right? And for many of these symmetric cipher systems, the two keys are in fact the same, and the systems are known as secret key or one key systems. In an asymmetric, or more popularly known as a public key system, it's practically impossible. It's believed to be practically impossible to deduce the decryption key from the encryption key. And I'm not really talking sophisticated mathematics here. The one that is used in the RSA public key system that I'll describe briefly at the end of the lecture really just depends upon the fact that it's easy to multiply two numbers together. That's an easy operation. But it is very difficult to find the factors of a number, to find those numbers of which a number is composed. That's what the operation is. I'll also be introducing another mathematical operation, which is the analogue of finding logarithms. Again, finding logarithms, as you I'm sure did at school and probably still do in your spare time, is a relatively easy thing to do, but there's a case in which the discrete logarithm, where you're doing it in modular arithmetic, where it actually turns out to be difficult. And we'll look at some examples of that. But first of all, let's look at the security of a cipher system and bring out some of the assumptions within the subject. Well, our diagram says that Alice and Bob must have a matching pair of keys, but it may be very difficult to reach that situation. You know, if you want to distribute keys, they'll have to meet up, or they'll have to have a secure channel of distribution. And the management of keys, the whole key life cycle, which goes through key generation, key distribution, key usage, key change, and key destruction, is absolutely vital to the security of any cipher system. And I don't apologise for harking on about keys. You know, if you write your PIN number on your bank card, you're just asking for trouble. But in the asymmetric case, there's a different problem. In the asymmetric case, the encryption keys for everybody is public. If I want to send a message to you, I look up a directory of your public key. I find your public key, I go to the publicly known encryption algorithm, I use your public key, the encryption algorithm, and in my message, I send a message to you. You use your private key in order to decode it. But the thing is, how am I really to know who's sending the message? You know, who does the public key actually belong to? So this is a question of authentication, and the danger of impersonation is something that we'll see. We can use certification authorities and digital signatures to try to resolve. Right. The problem of assessing the security of a cipher system is really exceptionally difficult. Well, it's not an exact science at all. And it is helpful not to ask for absolute security, but to ask for it to be good enough. In other words, to be good enough for the purpose for which the cipher system is intended. And a helpful measure when you're doing that is this notion of cover time, which is how long you want the communication to remain secure, and that will clearly depend upon the circumstances that you're dealing with. And how do you measure the cover time? Well, again, it's a very coarse sort of way of doing it, but a useful type of way of doing it is to say, well, let's attack the system by trying all of the possible decryption keys that there can be for it. Right? So that's a case of a brute force attack, and we'll look at some examples in the substitution cipher of how long a brute force attack would take by trying all the keys. But then there's an alternative way, using the structure of language, that you can attack the system very easily. But this at least is one way of trying to get some idea of the security of the cipher system. And what you normally do is you normally have got three worst case conditions. And the first one is that the cryptanalyst has a complete knowledge of the cipher system. Now, that doesn't mean that you have to make sure that the cipher system, you have to make public the details of the cipher system. You don't have to do that there. You could try to hide them in hardware. You could try to hide them in software. But it's a reasonable assumption to make is that eventually they will be revealed. And in the Polish cryptographer's attack on the Enigma machine, in fact, the French intelligence espionage services had found out the wiring structure of the routers, which were a key part of that machine. The Germans presumably didn't know that had been obtained. But worst case scenario one, worst case condition one, is very important to the manufacturers of cipher systems, because it removes from them the responsibility of having to keep their system secret. The next one is, you assume that the cryptanalyst has obtained a considerable amount of the cipher text. Right? And this is a reasonable assumption, because if Eve can't see any cipher text, then there's no point to have any encryption at all. And if Eve can see cipher text, then the worst case situation is that she can see all of it. And the third worst case scenario is that the cryptanalyst knows the plain text equivalent of a certain amount of cipher text. So that some particular way, perhaps by the structure of a communication for a letter, if you know that the letter always starts off with the date. The plain text therefore starts off with a date and perhaps ends yours faithfully all the time. And many military communications have got a very structured type of format. Then you know what appears in the cipher text corresponding to certain bits of plain text. Right? On the other hand, as I believe happened certain situations. World War II, the British would attack certain German light boys in order to be able to read the report of that attack, which was encoded using the Enigma machine, and they would know certain things like where the light boy clearly was located and at what time it was attacked. So that's an example of a chosen, can be thought of as a chosen plain text attack. What they're doing there is they're feeding the plain text into the cipher system and looking at the resulting cipher text. So one tends to look at all of these worst case scenarios when you're trying to assess cipher security. Okay, so let me turn now to the simple Caesar cipher, and we'll look at some of the ways in which we can attack it. And it's a very simple cipher. You may have used it at school, but I wouldn't advise putting much reliance on it. But I thought it's this nice picture from the web because it shows that it can be mechanized by means of a machine. What we have here, the 26 letters of the alphabet, and the Caesar cipher is really just a shift cipher. And what we have in this particular one is we've got the alphabet around the outside. So that, for example, Gresham College, what you do is you go to G on the outside of the ring, and if you find G, which is over here, then you encode G by the corresponding letter in the inside ring, which is in fact G shifted by 13 letters clockwise. So G goes to T, and then, or if we come right round to it, it's there, or on the outside goes to E. So this is a Caesar cipher with a shift of 13, and the reason it's a shift of 13 is because that's the diagram that I could find on the web, and I had to count out how much it was, but I really wanted to use a shift of 3. So here's my cipher diagram, and I want to use it now in the particular case of a Caesar cipher with encryption key 3. So here an encryption key is 3, so we're going to shift clockwise, thinking of the alphabet written round in a circle, clockwise by 3, so that the word message M then goes to P, shifting M by 3 letters clockwise, E goes to H, S goes to V, S goes to V, and so on. And just for the sake of symmetry, what I've done is to write the decryption algorithm out in a way that maintains symmetry. And I say that the decryption algorithm is rotate clockwise by 23, and that will work because if you rotate by 3 and then you rotate by 23, 3 plus 23 gives you 26, and 26 is going the whole way round and brings you back to the beginning. The advantage of that, if it is an advantage, is that the encryption and decryption algorithm are the same. It's the encryption keys and decryption key that are different. One of them is 3 and one of them is 23. Of course, you could write it the other way round, which is you could make the keys the same, namely both of them 3, but here you say rotate clockwise by 3, and here you say rotate anti-clockwise by 3. So different ways of writing the system out. Right. But the Caesar cipher is very easily attacked, and here I have got a cryptogram AFCCP, and that 5-letter cryptogram, I want to find out what it is encrypting, and I'm making the assumption that it is an English word. And what I have done here is to write down all the possible originating messages could be under the different encryption keys. So a possible originating message is AFCCP, where you just leave it alone. Another originating message might be this, if you shift it by 25, and if you look down at here, what you're essentially looking for is an English word, an English meaningful word, and there are in fact 2 of them, cheer and jolly. And it takes quite a while to find 2 5-letter English words that go into each other under a Caesar shift. Of course, you're going to listen to me for the rest of the lecture, but otherwise you should try it for a 6-letter word. So what we've done there, the point I want to draw out from this very trivial example, is that just by this brute force attack, we've immediately ruled out we've ruled out all but 2 of the keys. Right? So all but 2 of the keys are ruled out. We can't decide which one it is unless we either have more plain text or we have some knowledge of the context. And that's frequently what happens when you have a brute force attack, that you're not so much finding the keys as ruling keys out. Okay. Because it's going to be useful for later on, I just wanted to make this other point before that. The second bullet point down is that if you're able to do a known plain text attack on a Caesar cipher, you only have to submit the one letter. Because as soon as you know what any letter goes to, you know what the shift is. So Caesar cipher is totally vulnerable to a known plain text attack. If you know what A goes to, you know the shift. I just want to show you that it can be written as an additive cipher because I want to introduce modular arithmetic, and this seems like a very straightforward place at which to do it. I'm going to write the letters of the alphabet to encode them by the numbers 0 up to 25. A is 0 and B is 1 and so on up to 25. That's one way of doing it. Then if the encryption key is Y, you could describe the Caesar cipher as saying that you add X plus Y, you add the number corresponding to the letter to the key Y. But then, to take into account that we've got the letter's been written in a circle, what you then look for is the remainder modulo 26. So you divide in by 26 and find the remainder. And there's an example of it there. Suppose the encryption key is 18. Then if you want to encrypt J, the number corresponding to J is 9. 9 and 18 is 27. What's the remainder of 27 when you divide by 26? That's 1, and therefore J is encrypted as B. So that's really introducing modular arithmetic there. Okay, well, let me go to an example which shows that a large number of keys doesn't necessarily provide security, and that's the simple substitution cipher. A large number of keys is necessary for security, but it's not sufficient. So the key here is that you take the alphabet, there's the alphabet written out in alphabetical order, and then you put down below it some rearrangement, and that rearrangement is written in blue, and the key is this set of blue letters in this particular order. So in order to do the encryption, if we want to encrypt Gresham, notice the publicity that's going out all the time, not even subliminally. G goes to M, R goes to K, and E goes to I. Right. Now, so the encryption and decryption keys are equal. They're just this ordering of the letters. The encryption algorithm is you replace each letter by the one below it, and the decryption algorithm is you do the opposite. You replace each letter by the one above it. So let's look at the number of keys that there are. Well, the number of keys are just the number of ways you can write out the alphabet, the number of different orderings of writing out the alphabet, and believe me, there are a lot of them. There are 26 choices of which letter to put in the first position, 25 left then of which letter to put in the second, 24 of which letter to put in the third, and you keep multiplying them together and you get that number that is written down there. And I wouldn't even attempt to read it out, but it's approximately 4 times 10 to the power 27. 4 with 27 zeros after it, and a very large number. And I have worked this out. If you were able to try 1 billion keys each second, 1 billion keys each second, it would take nearly 13 billion years to try them all. However, one disadvantage of it, and the point I'm making here, is that these systems are a lot of the time used by people. The key's long and difficult to memorize, and that's often what forms the weakness of a cipher system. And remember, we're not able to write it down, or if we do write it down, we have to store it securely. We have to keep it safe. So one thing that is frequently done is to use a key phrase in order to generate the keys. Many people also do that as a way of remembering their passwords as well. Similar idea. So if you take the key phrase, again, Gresham College, free public lectures. What you do with the key phrase, one way of doing it would be to write down Gresham College free public lectures, but as you're doing it, only have each letter once so that you remove all repetitions from the key phrase. So if you were to go along it, Gresham, no letter has been repeated, COL, but then the next L of college, of course, already appears, so that is not inserted, that's deleted. Then the E has already appeared, the G has already appeared, the next E has already appeared. So the next new letter is F, and you keep on doing that, writing down each letter without repetition until you get to the end of your phrase, and then just fill in those letters of the alphabet that you haven't written down so far in alphabetical order. So it's a relatively easy way to remember how to generate the key phrase each time. All right, and here I've done one with, okay. But although it's got these large number of keys, a brute force attack would take such a length of time. It turns out that it's very, very easy to solve due to the statistics of the English language, or indeed any natural language. And here I've taken a table, an analysis of letters occurring in words listed in the Concise Oxford Dictionary, and the third column is proportions, with the baseline being the least frequent letter Q. All right, so this is telling us that E occurs nearly 57 times in this Concise English Dictionary, more often than Q. A occurs 43 more times, or 38 times. I 38 times more frequently than the letter. And as usual, it's probably easier to understand this visually. It's really saying, the way I like to think of it is that this is a fingerprint of the English language. Right, and the histogram here of the frequencies, the one on the left is the frequencies sorted by those which are most popular, so starting off with E on the left hand side, and on the right hand side I've just got the letters written out in the alphabetical order. And what I'm saying is that this histogram is essentially characteristic of any long enough piece of English text reasonably accurately. Right. So that then points to the weakness of the substitution cipher, because the substitution cipher does exactly what it says on the tin. A substitution cipher substitutes. So that, for example, if it substitutes E by W, and then you do a frequency count of all the letters in your ciphertext, and you find out that W is the most frequent, it's very likely that W substitutes for E. Right? And then you can look at the next four letters, so that here is an example where I've got a particular key that I'm not telling you yet, and I've written this message out using a particular, I'm telling you it's a substitution cipher, and then what is down below it in the table is the frequency analysis for this particular text. I've gone through it, very relaxing, counting how many times each of the letters occur. And then I've done a graph of it down here, so I've got the frequency diagram. Now that's just going to be the same, if I'm right, and that the statistics do work out, that as the histogram we had before, but it's just going to be jumbled up in some way. It's just going to be permuted in the same way the substitution cipher permutes it. So what I'm saying there, with that particular one, it's harder to see. That what we have is that this letter here, which I think is, that's the one we're going to initially substitute in for E, and then looking at the other four that are most popular in the histogram, substitute them in for the ones in the English language text, and we find out, and it comes out very quickly, that the key is the one that I introduced a little while ago, obtained from the phrase Gresham College Free Public Lectures, and the text is just the publicity for this particular lecture. Okay. Now, a few things you can perhaps think of as you're looking at that. I was very foolish in the sense that I'd left in the words in the ciphertext, and that's silly. You should all write it out in blocks of the same length, say of 5, because there only are a couple of one-letter words in English. So if you know what the word length is, if you leave them in, you've got a good start. Question that's sort of obvious is, how long is long enough? How long should the ciphertext be in order to use a frequency analysis attack on it? And it seems that 200 characters is long enough, and I've had students who are able to do it with, about 100. Because of their perseverance and how quick they are at looking at possibilities, or rather ruling out possibilities. We've said it's vulnerable because of the structure of language, and historically there were various other ways of trying to get around this fingerprint, one of which in a very famous cipher called the Playfair cipher encoded not letters but pairs of letters, and had a particular way of doing that there. But pairs of letters are subject to exactly the same statistical analysis as letters. Certain bigrams appear with particular frequency much more often than certain other bigrams. So general substitution things, once you know that one of them is being used, are very straightforward to attack. So a large number of keys is not sufficient in order to assure security. So what was the problem if you think back to what's been going on? The problem was Caesar cipher, it was subject to a known plain text attack, only one letter. Substitution cipher, it had this fingerprint attached to it when you applied a frequency analysis. What you want to do is to try to make that frequency histogram flat, that all the letters in the ciphertext should appear equally often. And various ways of doing that come under the general heading of polyalphabetic ciphers, where essentially what you're doing is you're using more than one substitution cipher. The example I'm going to be looking at in the moment, I'm going to be using 8 substitution ciphers. In the Enigma machine with 3 rotors, it was something like 17,576 substitution ciphers, one after another. And we'll see in the example I'm going to show you how that flattens out the histogram and therefore tries to conceal the fingerprint. So let me look at one particular example, the Vigenère Cipher, which is going in this case to use 8 substitution ciphers. What you do is you take your plain text, you have your plain text here, age 26 Vigenère. Right. Then I take a key. I'm going to take the key as being Charles V, and if the key isn't long enough for your message, what you do is just repeat the key, Charles V, and then I don't need to use all of it. And then we use the Vigenère table, which is a table of substitution ciphers. And if you had time to look at it for long enough, they are just simple Caesar substitution ciphers, but there's a table of them. And then what I do is to for the letter A, to encode the letter A, I'm going to use row C. I look to the key, and when I use row C of the table, it tells me that this is the substitution cipher to use. So in order to encode A is going to be encoded as C. So the A of aged is encoded down to C. Now the next letter I want to encode is G, and the key tells me that I should use row H of the thing, and row H is, I hope you're appreciative of the effort I've gone into the graphics of this, because otherwise I was going to have to ask you to close your eyes and imagine it, but you mightn't have opened them again. So there, anyway, this tells us to use row H, and we want to encode G, and if we go from G down to here, it's encoded as N, which is done here. So times like this you realize you've made a mistake on it. But we haven't. Then the next one we want to encode E, and the key tells us to encode A, and row A, and the thing that we're trying to encode is E, and of course just goes to itself. Right. Now let's see what that does to the signature. Let's see what that does to the histogram. So this is some little background about Vigenère, and what I've done below is to do a histogram of the frequency analysis of the plain text, and that's what is in the upper histogram. And down here I've done a monoalphabetic substitution on it, and as we know by now, all that does is just to permute, just to interchange the bars of the histogram. But down here we've got the Vigenère ciphertext. So if you do a frequency analysis on it, on the Vigenère ciphertext, once that's encoded, notice how the histogram is much flatter. The letters are occurring much more evenly across it. Ideally, you would like them all to appear as often as possible. So you think that's good. That's that's progress, and of course it is progress. But again, the ingenuity of people attacking these ciphers, and you can realize it yourself. If you know the length of the key word, you're home. Because if the keyword is of length 8, it means that the first letter and the 9th letter, and add on 8 and 9, the 17th letter, all come from the same substitution cipher, because the key has started to repeat. And the second letter and the 10th letter, and this one's easier, and the 18th letter all came from the same substitution cipher. And the third letter and the 11th letter, and so on. And we know how to break substitution ciphers. You can now do that with your eyes closed. So all you have to do is to find the length of the key. And you could just try by guessing, but so on. But there's a better way of doing it, which was discovered by Charles Babbage. And what he did was a reasonable idea. He looked for repetitions of letters in the ciphertext. Looked for repetitions of longer, the better, but particular group of letters in the ciphertext. And then he argued as follows. If we do have repetitions, it might be the case that what's happening there is that the same letters in plain text are being encoded a distance apart, which is a multiple of the key. So you've got repetitions within your ciphertext. You look at the distance between them, and you say it's very likely that the distance between them is going to be a multiple of the length of the key. So you find out what numbers divide into that, and you try those various possibilities for the key, and you can run through it relatively quickly. You certainly can if you can use a machine on it. Okay. All right. So that brings me to one of the most famous polyalphabetic ciphers, the Enigma Machine, which has, let me just go forward to remind myself and then back again, 17,576 substitution ciphers, rather than the 8 that we just had a moment ago. And it's possibly best known for the activities of the cryptographers cryptanalysts at Bletchley Park, Alan Turing and colleagues there, where they had a very comprehensive way of breaking it. But I won't tell you perhaps a less well-known story of how the Polish cryptanalysts attacked it. But first of all, to describe what happens, if you look at the picture on the left, in order to use the machine for encrypting or decrypting, this is a keyboard here, and you press the letter on the keyboard key corresponding to the message in front of you, and then there's a little lamp board that lights up. So you press the letter A, and some letter will light up on the lamp board, and that's what the encoding of it is. And it's an electromechanic rotor one. What happens is that when you press the letter on the keyboard, an electric current is flowing through the machine and causing the light to light up. But what is it flowing through? Well, it flows through 3 rotors, and I think you can see here, I've tended to indicate them. Here's the letter A being pressed, and these rotors are touching each other. There's little studs on each side of them which make contact, and they are cross-wired. All right, there's an internal wiring for them. So the current coming in here will go out there, will go across to here, go across to there, come down to there, and then they're reflected at something which is called the reflector, and here it comes back down across here, and so on. So you've got your rotors. There's internal wiring, which was discovered by the French espionage. So the Poles knew what the wiring was, and that coincides with our, remember, worst case scenario 1 about the Cipher System, to assume that everything about it is known. Now, the core thing, 2 things I want to mention now, is that the thing is that you press the letter A and the lamp for G works up, lights up, but then the first rotor rotates. It clicks on, it rotates by 1 click. Okay, so that if the next time you were to press A, there would be a different set of wires that would go through. In fact, the diagram is done such that this rotates like that round up to here, which is why this horizontal line now appears at the top. So there's a different pathway to be followed through, reflected back, so that this time A will be encoded as C. And if you were to press A again, the rotor would click round once more, and there would be a different encoding. And then once this rotor has gone round 26 times, this clicks once, this rotates once, the middle one. And then once the middle one has gone round 26 times, this goes round once. Okay, so it takes 26 times 26 times 26 for it to get back to the state that it was in before. But that's not all. In order to get the number of settings of the system to be much larger, there's introduced a plug board here, where what a plug board is a bit like an old telephone exchange, if you remember, where you sort of have electrical wires and you connect two things together. And what they do in the plug board is they choose 6 or 7 pairs of letters to connect them together, so that as you press the key, there's a swapping over of the letters before they go into the rotors. Then they're reflected back through the rotors, and then they're reflected possibly at the plug board again, and then light up the lamp. And I'll show you what the numbers are in a moment. Okay, so they're the various components of it. And of course, the other thing as well is that the rotors are up here at the top, and you can see there's another thing called a ring round the outside of them, but as Andrew Hodges says in his book, that's a tedious complication. But what you can do is there are letters along the top which gives you the setting of the rotors, which way to set them off to start up with. And I should also say that the rotors can be put into there in any order. All right, so quite a number of variations. And of course, I'm just giving you one example of it. There were various kinds of Enigma machines with more than 3 rotors, 4, 5. I think some of them may have gone up to 8. I'm not sure. And there are probably people in the audience who know a lot more about these than me. But I'll take this one as just an example of what goes on. All right, so let's look at just some numbers. It's polyalphabetic, first of all, 17,576. In each state, the Enigma, the substitution alphabet's a swapping of pairs of letters, and there's a particular characteristic of this machine. It can never encode a letter into itself, and that formed the basis. One can think of that as forming the basis of Turing's attack of it in Bletchley Park. That simple observation doesn't encode a letter into itself. And there's a very good discussion of this in Tom Corner's book on the pleasure of counting, where he brings you through the sort of mathematics underlying Turing's attack and Turing and the colleagues' attack. Right. So let's just do counting. The number of rotor settings is this 26 by 26 by 26, but you can have the rotors in any one of 6 orders. You can choose which way to put the 3 of them in. The plug board connecting 7 pairs of letters, and that's quite a fun thing to do, to count how many ways it's possible, if you have 26 letters of the alphabet, to connect them in pairs. And the answer is that number that I've written down. And I gave up when I'm going to calculate the total number of keys. It's just all of those multiplied together. Okay, so we've got all of those large number of attacks. Let's try to see what the possibilities are. And it was broken by Rajewski. This picture is probably taken in 1932, the year he first solved it. The point about his attack was how it was used. So let me go to that. All right. Code books were distributed to give the day key. So all units using it had a code book. The code book would say you have to get the rotors in this order, and you have to turn them so that they're in these positions. You have to use the plug board to connect these letters. That is in a code book that is distributed to every Enigma machine, I suppose. But then the way of using it in the 1930s was that the day key was used to transmit a new key, which the Alice and Bob would then use, whether Alice and Bob with their names, I don't know, would then use to transmit a new key that would be used for all further subsequent communication. So for example, suppose the day key was my initials, RGF, and the sender uses it to transmit the chosen new key. The sender decides to choose KJE, and it was sent twice. It was sent twice because they were worried about presumably corruption and transmission errors, so to be able to pick that up. But that was the weakness. That was the undoing. That was how Rajewski managed to crack it. So with the day key setting of RGF, we've got KJE transmitted, and it'll come through as something. Then both sender and receiver switch their machine to have settings KJE and communicate on from that. Now the thing about it, Rajewski seemed to know very little. He knew the internal wiring, he knew the machine. But the only thing that he didn't know is that On a given day, all the messages that were intercepted, the first 6 characters were sent using the same key. They were sent using the day key, the key in the codebook. And he knew something more. He knew that in all of those messages, the first and fourth were encodings of the same letter. They were related. Just use the word. There was a relationship between them. The second and fourth, the third and the sixth of the first 6 letters in every message sent on any particular day. So here is an example of just 4 messages. And this repeats what I've said. M and S are encodings of the same letter. They are related. N and Y are encodings of the same letter, as are K and N, E and Q. And I'm starting to write that in a table here. This is saying that E and Q, there's E and there's Q, they're related. I'm saying that K and N are related. There's K and there's N, it's related. I'm saying that N and Y are related. Have I done that? No, N and Y. I'm saying that M and S are related. Now, if you've got, as you would have, lots and lots of messages coming through, you examine the first 6 letters of them, you're going to be able to complete that table, and what we've got is that done down here. That A and L are related, B and G. In other words, that's saying that you've found some message in which A is the first letter and L is the fourth. Right. This is saying you found some message in which Q is the first letter and D is that. So what you've got here is a rearrangement of the alphabet down below with that relationship, and then you do something quite clever, and it's related to the notion of a mathematical object called a group, which actually underlies so many of the ideas that I'm going to be mentioning. In fact, will be part of the conversation next time. And what he did was he just started to unwrap what's called the cycle structure of what's below the line. So we would start off with a letter here. A goes to L, then L goes to W, W goes to F, F goes to M, M goes to S, S goes to J, J goes to C, C goes to R, and R goes back to A. So you've got this cycle going from A up to A, which has got 9 links. Then you look at a letter that doesn't appear here, such as B, and you do the same thing, and you get that that's a cycle of length 3, and this is a cycle of length 7, this is a cycle of length 7. The amazing thing is that these cycle lengths, 9, 3, 7, and 7, those numbers, those cycle lengths, are independent of the plug board settings. If you have a different plug board setting, okay, you'll get different letters in the cycles, but their lengths will be the same. And you will have a cycle structure for the 2nd and 5th letters, and you will have a cycle structure for the 3rd and the 6th letters. So what Rajewski and colleagues did was they spent a year putting the rotors in all the 3 different orders, adjusting them to all the different positions they could, and they drew up the table of all the different cycle settings that there were for all the different 17,576 rotor settings. When they got a message through, particular day, they looked to see what the cycle structure was, they looked at their table of what it was, they would know what the rotor settings is, and then they decoupled the plug settings from the rotor settings, and then it actually is fairly straightforward to determine what the plug settings are. Quite remarkable. And I think quite pretty, because it's technically easier than what Turing did, but it does show you how human ingenuity and analysis and mathematics. Rajewski was one of the first sort of mathematicians that were recruited to be involved with this. Right. Of course, it's highly dependent on the way it was used, and it was no good once they changed their system here. So coming to modern algorithms, where you have information represented using bit strings within a computer and different ways in which you can do it, encoding systems really depend upon by modifying the bit codes. And there's a system called XOR, which is a way of adding together the only 2 numbers that you have are 0 and 1, and this is essentially addition modulo 2, which is bringing modulo in. And down here I have, for example, a message 10011, and this is the key for it, 11001, and you add these numbers modulo 2. Or the way I like to think of it, which is nicer, is that if you've got a 1 in the key stream, it changes the letter above it. If you've got a 0 in the key stream, it leaves the letter above it alone. So here's a 1 in the key stream, so it changes that letter into 0. Here's a 1, it changes that letter 0 into 1. Here's a 0, it leaves that letter alone. Here's a 0, it leaves that letter alone. Here's a 1, it changes that letter. And that's used in particular in cipher systems and in a stream cipher. Here, what you get is, again, it comes back to that Charles V using the key idea. You have a short key and you have various ways of generating a long key string that you then combine with the message. Okay, and this is the thing that's used usually to digitize voice communications, because it doesn't have this error propagation. If you make a mistake in coding one digit, it's not going to affect any of the subsequent ones. But it is vulnerable to a known plain text attack, because if you can dictate what the plain text is in order to be encoded, then it can then you can try to identify what the rule is identifying the key stream. So there's that disadvantage to it. And I think originally that known plain text was used in the system was initially used in these identification friend or foe radars. To try to avoid, so if you're doing data encryption, or if you want to store data in that, a cipher system is not a very good way of doing it, because you're able to recover portions of it. A better way of doing it is to use a block cipher. So you choose a block length and you encode the various blocks of it. But remember our example back to the substitution cipher. If you've got enough, you'll be able to start to build up the statistics of what the encoding is, and that leaves you vulnerable to substitutions. Once you know the corresponding plain text and cipher text, maybe just substituting one for the other will be all that you need. You needn't even need to know what the key is. So there's systems, various ways of getting error propagation coming into it. One of them is called cipher block chaining. And all that happens here, the only thing you need to take out of this complicated sort of diagram is you've got the plain text broken up into blocks along the top. But when it comes down here and it's encoded, the encoding of the first block forms part of the encoding of the next block. The encoding of the second block comes up and forms part of the encoding of the third block, which means that a change in the message of just 1 or 2 letters earlier on will change all subsequent letters quite considerably. So you get this massive ripple effect going through, and it helps to guarantee the fact that a message has not been interfered with. Okay. So if I come to this very important and influential paper by Whitfield, Diffic and Martin Hellman on new directions in cryptography, it does say in its introduction the 2 kind of problems that they were concerned about addressing. And the problems they're concerned about addressing is the need for secure key distribution channels, because this is an expanding world, expanding number of objects that are communicating with each other, and some way of supplying a written signature. And the paper, which I've given the reference to at the end, is well worthwhile reading. It's very accessible and it's very thoughtful, and it's written from the perspective of 1976. So I've given a web reference for it, so you'll be able to just pull it down and have a look at it. And it's got a nice sort of historical section at the very end of it. Okay. All right. Turns out that what they need to do is to find something that's easy to do one way but difficult to do the other. And the thing that they use here are called discrete logarithms. Now, ordinary logarithms are relatively easy to calculate. In fact, one of my predecessors, the first Gresham professor of geometry, Henry Briggs, calculated 30,000 logarithms to 14 decimal places. And real logarithms are relatively easy to calculate because they behave sensibly. If one number is bigger than another, the logarithm is bigger. Okay. But discrete logarithms aren't like that. Here, for example, pick a prime, say 17. The reason I'm picking a prime is that, again, the integers 0, 1, 2, 3, 4, 5 up as far as 16, because 17 is a prime, form one of these group things that I'll be mentioning next time. And then if you look at it, if y equals 10 to the x, if the mod 17 weren't there, the rest of the sentence is one you've probably seen a lot of times. If y equals 10 to the x, then x is the logarithm of y. Right? But here we're saying if y equals 10 to the x mod 17, what we mean is that when you work out 10 to the x, I'll show you in a moment, then you call x the discrete logarithm of y. So here, for example, what are we going to have? Look at 10 to the 7. It's easy to calculate 10 to the 7. Divide 17 into it, and the answer is 5. So the discrete logarithm of 5 is 7. Discrete logarithm of 5 is 7. Now here you come 10 to the 3. 10 to the 3, work out what it is. It's 1,000. Divide by 17, and the remainder is 14. Right? So the discrete logarithm of 14 is 3. But notice immediately, they're sort of behaving strangely. 7 is the discrete logarithm of 5, but 14 is bigger, but its discrete logarithm is 3. So the discrete logarithms don't go all over the place. They jump all over the place. And the crux that you have to take from that, it's quite a lot there to absorb if you haven't met it before, is that knowing the red numbers, it's easy to calculate the blue. Right? All you have to do is to multiply a certain power of 10 and divide by 17 and find the remainder. But it's much harder if you know the blue number to find out what the red number is. But it's hard to find x if you know y. For example, 8 equals 10 to the x mod 17. What's x? The answer is in the handout. But it mightn't be right. Okay, let's see how Diffie Hellman used. That's the core thing. It's a one-way function, a trapdoor function, easy to fall in, very hard to get out. Okay. Another example that's usually given that I find quite helpful is that imagine you're in a room, locked in a room with a copy of the London phone directory. Somebody shouts to you the name and address of somebody and asks for the telephone number. You look it up because the names are given alphabetically, and you hand back the telephone number. Somebody tells you on the other hand, if somebody tells you what the telephone number is and asks you what the name and address is of the person, hey, hold on, all right? Okay, so that kind of sorting a question. So it's discrete logarithms that are used. Here I'm just repeating essentially what was said before, but knowing why it's hard to find x. Now let's see how Alice and Bob can use that in order to decide upon a key without meeting or without using a secure courier, and in fact do it on a communication channel that Eve can listen to. And they don't care that Eve is listening because the discrete logarithms are hard to calculate. So the way that they did it was that here we have two discrete logarithmic calculations I've got here. Alice's private key is 7. Alice's private key is the discrete logarithm of 5. Her public key is 5. So she publishes 5, but only she knows that 10 to the power of 7 has got a remainder of 5. The numbers are naughty. I hope you appreciate that this is done with numbers of 100 decimal digits, 300 binary digits, and so on. Now Bob's private key is 3 and his public key is 14. In other words, Bob publishes 14, all right, but only Bob knows that you get 14 as being the remainder of 10 to the 3, 1,000 divided by 17. Right? So here I'm just saying 5 to Bob. And then the algorithm to form the shared message is here. The message key for Alice is going to be the public key of Bob, right? The public key of Bob to Alice's private key. The message key for Bob is the public key of Alice to Bob's private key. Right? And the amazing thing is that the mathematics shows you that they're the same. The reason they're the same is because if you had a chance to unpack, as you will do when you go home, the slide, you will see that they are both 10 to the 3 times 3 multiplied by 7 mod 17, and the other one is 10 to the power of 7 times 3 mod 17. So they've shared this common key 6, and that's the one they shall use for subsequent messaging. Okay? All relies upon this this business of being able to find the the difficulty of doing discrete logarithms. And then just to finish, when we look at public key systems. The idea about a public key system, this is our Cipher system just done another way from this particular source. Everything here is public except this. Everything in that diagram is public except that. And the most popular, very important one is the RSA public key system, devised by Revest, Shamir and Adelman here. And it's named after their initials, and I quite like it having it here on a t-shirt here, where you can put it, and it's just an algorithm. And it really is quite nice. It describes it quite nicely. You choose 2 big primes, 100 decimal digit, it may even be more than that, it's presumably going up all the time. You form the number n equals p times q. It's very easy to do that, to multiply 2 primes together. All right. Then, this is still Bob doing it. You take the number p minus 1, q minus 1. That's the number you're going to be divided with to find remainders. And you find 2 other numbers. And again, it's reasonably easy to do this, to find 2 numbers, E and D. E for encryption, D for decryption, that leave a remainder 1 when divided by that. Too many details coming at you to absorb it. But just notice what the steps are. Then what do you publish? Well, you publish your public key n and the key E for encryption. Then to encrypt, you raise your message m to the power of E and find what the remainder it has when you divide by n. In order to decode, you take the ciphertext, the C, you raise it to the D power, and you find what its remainder is to the power n. And that works. One thing undoes the other thing, and that's the reason for that is because that the remainders of this particular number here again form one of those mathematical objects called a group, and that these 2 operations do each other. If you raise m to the power of E and then take that result and raise it to the power of D, you get back to where you start. The same as we had. The example I had before was 10 to the power of 3 times 7 and 10 to the power of 7 times 3. And you can use that idea to do I've just written out in more detail there, to form, for example, a digital signature. And the core thing in that, when you have a look at it later on, is that I'm sending a message here encoded using my private key. And you can decode it using my public key. So you know it must be me, because I'm the only person who could have used my private key to encode it, because you're decoding it using my public key. Brilliant, very clever, and very simple. Okay, then, to finish now. And I have to say, although I've used Diffie Hellman, the 76 paper in my discussion, it turns out that many of the main principles and techniques of public key cryptography had been developed earlier in the 1970s by James Ellis, Clifford Cox, and Malcolm Williamson at the UK government's Communications Electronic Security Group. The work was classified and not made public for over 2 decades. And it's interesting, I think, to speculate what else may be secret at the moment. And a lot of work, research, money is going into cryptographic research, because the secure communications are becoming more and more important because of e-commerce and various other reasons. And it doesn't just matter to large organizations, the banks and commerce, retailers and so on. It matters to ordinary individuals. And in order to show you how topical this topic is, in The Guardian last Saturday, in the money section, the headline was, "Pay us £200 or we will lock your computer forever." And apparently the thing that's being downloaded they're calling ransomware. And if you inappropriately click on something, it encrypts your files using public key cryptography, and then you get a message saying that they'll send you the private key if you will send them £200. Otherwise you'll never be able to get it, as I've tried to convince you of here. So if there's one thing I hope that you've learned from this lecture, is that when you get home, back up your computer. So look forward to seeing you. This is in the handout. Also add on to that The Pleasure of Counting by Tom Corner, and hopefully see you at Symmetries and Groups for Christmas treat, an early Christmas treat, Tuesday the 19th of November. Thank you.